All right, so welcome everyone. This is going to be the first of our online lectures. This is going to be kind of how things go from here on out. So this first lecture I'm just going to upload on YouTube, but the plan is going forward I'll try to stream these probably through Zoom or maybe through some other Blackboard Ultra or something along those lines. But I'll try to stream these so that I can answer your questions along the way, and it's not just you looking at a video screen for an hour or however long these lectures are going to last. But other than the fact that these things are online, the structure of this class is going to be essentially the same. I'm going to do a quick recap of what we did last time, and then I'm going to move on to some new material for today. So the first thing I guess I should do is a recap. So let's recap what we did on Monday. So in class on Monday, we introduced triple integrals. So we have been doing integrals up until this point, and we've sort of been focusing on double integrals, integrals over regions inside of R2. And the only real big difference between triple integrals and double integrals is that our functions now depend on three variables. Okay, so what does that mean? That means our functions fxy have been bumped up to fxyz's, and we're going to be integrating over volume elements over regions inside of R3. So they're evaluated the same way using iterated integrals. So once you choose an order of integration, so say for example dz dx dy, then what you do is just put in your fxyz, dz dx dy, and the sort of hardest part is always finding the bounds for these functions or for these integrals. So in principle, doing the integral at any given point is just a single variable integral, kind of one at a time. So if you remember your Calc 1 or Calc 2, you're not going to have too much trouble. But it's usually finding the bounds that's the hardest part. So if your dz integral is the first one, then your bounds can depend in general on functions that depend on the outer two variables of integration. So the next one in this case is dx, so there's nothing stopping our x bounds from depending on y, because y will eventually be integrated out. And then finally, our y bounds can only really be numbers. So how does this work is, you do your first integral, you integrate z, and whatever the answers you get in the antiderivative for z are replaced by p's and q's of x and y. So after doing the first integral, you're left with a double integral depending only on the variables x and y, and then again you do your dx integral and you'll have some function that depends only on y. And finally, when you integrate out the y variable, you should just hopefully get a number out in the end. And so finding bounds is usually the hardest part. So our strategy for finding bounds is you do the innermost first. So in this case, our dz bound, what you do is, say, let's go back to the example we did from last lecture. If I'm considering this surface, which is defined by the equation z equals 4 minus x squared minus y squared, the way I find my z bounds is I start off way far in the negative z-axis. I move up, 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 until eventually I hit the bottom surface here, the z equals 0 surface. And that's my lower bound. Move up through the surface until eventually I hit this top guy right here, which is the surface z equals 4 minus x squared, and that's my upper bound. And then I leave here. And so when I go to do these integrals, my x and y integrals I have to worry about later, but at least my dz integrals, I go from z equals 0 up to z equals 4 minus x squared minus y squared. And then how do you, you can have some function in here if you want, or you're just calculating volume, you just put a 1 or whatever. Then how do you find your dx and dy integrals? So now, after you find your dz bounds, your dx dy bounds, the way I think about it is I draw, this little flashlight here, and this flashlight, what it'll do is it'll sort of pick out the shadow of this region inside the xy plane. So in this case, the shadow in the xy plane is this semicircle right here. So the shadow in the xy plane tells me what my xy bounds should be. So in this case, my xy bounds go from 0 up to, so I mean, once you find your innermost bound, it just boils down to a double integral problem. So if you know how to find bounds for double integrals, you'll know how to find bounds for the outer two integrals. So in this case, the dx bounds go from 0 up to root 4 minus y squared, and then dy goes from 0 up to 2. So why is it 4? Well, we need to know what the radius of the circle is. So the radius of the circle is determined when this surface here, 4 minus x squared minus y squared, intersects the x-axis, or the xy plane rather. So when does this intersect the xy plane? That's when z equals 0. It's 4 minus x squared minus y squared. And this tells us what the equation of this curve is right here. And so that curve is giving our upper bound for y and x. Okay, so finding our bounds for the outer two integrals is pretty much just an exercise in double integrals, but finding our bounds for the inner integral is a little bit more complicated because we have functions that could potentially depend on more than just two variables. And then the last thing that we mentioned last time was that you can calculate volume as the triple integral of 1 dv over region t. So this will give you the volume of t. Or if you want, you can do the double integral of a function f of xy dA, and this will give you the volume between the surface z equals f of xy and z equals 0. So if our region that we're interested in taking the volume of is something that's living between some surface z equals f of xy and the plane, so say this region, for example, then you can either calculate that region as this double integral or as this triple integral, and you'll get the same answer in either case. And in fact, the way you go in between the two is you notice that if I write dv in this order of integration, or really just making sure that dz is the first integral that you evaluate, you just pull down this f of xy, and that'll give you the double integral that's calculating that same volume. All right, so that's a recap of what we did last lecture. So what we're going to do in this lecture is we're going to move on to section 3.6. So in section 3.6, we introduce two new sets of coordinates, so cylindrical and spherical coordinates. So how do these sets of coordinates work? So they're kind of like 3D analogs of polar coordinates. So what do I mean by that? So in R2, right, when you were dealing with some regions or functions that were rotationally symmetric about the origin, sometimes it was convenient to work with polar coordinates. So you would replace x and y with, instead of x and y, you'd replace them with r and theta. And if your functions really depended on the quantities like x squared plus y squared, then your integrals ended up simplifying pretty greatly. Okay? And so what's going on in R3 is that there's kind of two different choices that you can have for r and theta. And this boils down to the difference between cylindrical and spherical coordinates. So what I'll do first is I'll focus on cylindrical coordinates, do a few examples using cylindrical coordinates, and then I'll move on to spherical coordinates, which is a little bit more complicated, but just as helpful. So let's first do cylindrical coordinates. So cylindrical coordinates should be a new set of coordinates, so some new set of numbers that describe points in R3. So I can describe a point in R3 using x, y, and z. So if I just pick this point, say x, y, z here, what I can do is I can find out what its x coordinate is, what its y coordinate is, and what its z coordinate is. You know, z coordinate is say somewhere right here, and that's going to give us essentially what that point, that's going to uniquely classify that point in R3. Okay, so let me just finish off this little cube right here. Okay, so this point is uniquely classified by the numbers x, y, and z. So sometimes though there's regions or functions which are cylindrically symmetric. So what I mean by that is they only depend on x and y through the quantity x squared plus y squared. So this is exactly the same as functions or regions that are rotationally symmetric in 2D, but now we have this extra z-axis to deal with. So they're essentially functions or regions that depend on the distance away from the z-axis and essentially nothing else. And so how do we do essentially polar coordinates in R3? We're going to introduce some new sets of coordinates. So we're going to describe all of our points in R3 using r, theta, and z. And let's give our definitions for r, theta, and z. So r in this case is going to be exactly the same r as last time. So r here is essentially the distance that this point makes with the z-axis. So r is going to be the root of x squared plus y squared, square root of x squared plus y squared. Theta is the same as well. So theta, as before, was measured from the x-axis, counting upwards counterclockwise, and theta is the same as before. So theta is going to be using the same formulas as before, tangent inverse of y over x. And then finally, how do I finish off describing a point in R3? Well, I need one more set of coordinates than I did in R2, and what I'll do is I'll just tell you how far up or how far down this point is from the z-axis, or from the xy plane, and that's going to be our z coordinate. And z is really just the same as, z. We're not really doing anything new. So these are cylindrical coordinates. New way of describing a point in R3 using the quantities r, theta, and z. So let's just say a few more words. So because these are the same r, thetas, and z's from polar coordinates, we know how to go in the opposite direction as well. So we know how to describe x, y, and z in terms of these coordinates. So z is just z, and then x is r sine, or y is r sine theta, and x is r cosine theta. Okay, so nothing special there. This is how you express r, theta, and z, and this is how you express x, y, and z in the other set of coordinates. Our bounds, r is always going to be positive, just to avoid double counting. Theta is always going to be measured between 0 and 2 pi, again to avoid double counting. And z, there's no bounds on z, so z can be anything between positive infinity and negative infinity. And then finally, we need to describe what our volume element is in terms of polar coordinates, or in terms of cylindrical coordinates. And how do we calculate the volume element before? Well, what we did was we did a little bit of trigonometry. So if you recall from last lecture, or maybe a few lectures ago, the way we figured out what the area element in polar coordinates was, as r dr d theta, was we took a little bit of a sliver of a d theta, a little sliver of a dr, and we figured out what the area of this little cube was, or this little area element was in terms of dr and d theta. And it took a little bit of trigonometry, and we were able to determine that it was r dr d theta. And this r right here is telling us that as we move further away from the origin, our volume or our area elements get bigger and bigger depending on how far away, and it depends on how far away I am linearly. What's going on in R3 is it's going to be exactly the same. In fact, it's going to literally be the same formula. It'll be r dz dr d theta here. The only difference is that we have an extra dz. And you can essentially figure this out using the same calculation that we figured out the area element in section 3.4. So essentially figuring out what this dz is, or what this dv is kind of something that we've already done. But once we know what dv is, we can sort of treat triple integrals using polar coordinates or using cylindrical coordinates in exactly the same way as we did before. So let's do an example and see how that works. So let's try to calculate the integral, or let's rather try to find the volume of T, where T is the region enclosed by the surfaces z equals root x squared plus y squared, and z equals root 8 minus x squared minus y squared. So z is between these two expressions. And just as essentially all problems in Calc 3 go, the strategy for solving this kind of problem is to first draw the picture. So let's draw the picture. What's going on? So z is going up again. So what does this surface look like? This surface is given by a cone. So you can see that so it's really just the upper cone. So if you square both sides, you get z squared equals x squared plus y squared. And if you go all the way back to the quadratic sections of this class, you'll recall that that is the expression for the double cone, but now we've actually selected out the positive square root here. So we're actually only describing the upper cone. Okay, so what is this describing? This is, if you again square both sides, you're essentially looking at a sphere of radius square root of 8, but because we've again selected only the upper cone, or rather the upper square root, the positive square root, we're only talking about the positive hemisphere. So this is the upper hemisphere of a sphere of radius root 8. So if you draw this, okay, so the cone just kind of looks like a cone, okay, and the hemisphere is going to be something like this guy right here. Okay, so this is maybe not the best picture, but it at least gives us an idea of what our bounds should be. So what's going on is that these two surfaces intersect, let me use a different color, intersect in some circle of radius something. We're going to have to figure out what that radius is at some point. And anything which is contained inside this maybe ice cream cone shaped figure, where the sort of the top part of the ice cream is given by the hemisphere and the cone itself is given by the cone. Anything in this region is inside of the area or the region enclosed by these two surfaces. So we want to figure out what that volume is. So the volume of T, as we know, is just going to be the integral of 1 dv over T. Okay, so we need to evaluate that triple integral. So how do we evaluate that? Using polar coordinate, or using cylindrical coordinates, dv is replaced with r dz dr d theta. And we need to realize what dz bounds are, dr bounds are, and d theta bounds are. Okay, so let's go about that way. So the z bounds are evaluated the same way as the z bounds as before. So you start off in the negative z-axis, you kind of walk upwards until eventually you hit the first surface, and that's going to be our lower bound. And the first surface that we encounter in this case is the equation of the cone. So our lower bound will be given by this cone. The only difference is we need to now replace x with r squared cosine squared theta and y squared with r squared sine squared theta, and we see that z is square root of r squared, or just r. So our lower bound is r. What's our upper bound? Our upper bound Well, you keep on living in the surface until eventually you hit your ice cream part of the ice cream cone, and then you leave, right? So our upper bound is given by the equation of the surface where we leave. And we're leaving right here when we hit this equation of this surface. And expressing that in terms of r and theta, you get x minus r squared, or 8 minus r squared, and that's going to be our upper bound for z. Okay? So our z bounds go from r to root 8 minus r squared. What about our r bounds? So our r bounds we find by drawing that same little flashlight. So we draw a little flashlight up here, and it's shining some light. And what we see is we see the shadow in the xy plane is essentially given by the equation of this circle of intersection between the cone and the hemisphere. So we need to figure out what that intersection is, because once I figure out what that intersection is, the region in xy plane is given by that circle of radius r. Okay, so let's realize what that intersection is by just solving these two equations simultaneously. So root x squared plus y squared is supposed to equal root 8 minus x squared minus y squared. And that's the same thing, squaring both sides, as giving me 2x squared plus 2y squared equals 8, which is the same thing as x squared plus y squared equals 4, right? So I skipped a few steps, but I see that the equation of this curve right here is x squared plus y squared equals 4, which is a circle of radius 2. So our r bounds go from 0 up to 2. And then we don't have any restrictions on theta, so our theta bounds go from 0 to 2 pi. And here we've essentially set up our integral that we want to evaluate to figure out what the volume of this region T is. So the volume of T is equal to the triple integral from 0 to 2 pi, 0 to 2, r to root 8 minus r squared of r dz dr d theta. And I'm not going to actually evaluate this completely, but I'll at least do the innermost integral. So evaluating the innermost integral, 0 to 2 pi, 0 to 2. There is no z's anywhere. Okay, so the antiderivative is just going to be r d or rz, and z will be replaced by root 8 minus r squared minus r squared and dr d theta. Okay. So if you want to go further, okay, it's not so bad. You may have to do a u sub here. You may have to split this integral up into a sum. But in the end, you go through the work. It's not that much work, but it's something that I don't really want to do right now. You get 32 pi over 3 times root 2 minus 1. Okay? And that's what your bounds are. Or rather, that's what your number is, the total integral. So what we're going to do now is we're going to introduce a new set of coordinates. So let's go back. So this is the section on cylindrical and spherical coordinates. So we've kind of treated cylindrical coordinates. Now what we're going to do is we're going to introduce spherical coordinates. So cylindrical coordinates weren't so different from polar coordinates, but spherical coordinates we're going to introduce a little bit of complexity here. So how do spherical coordinates work? We want to describe essentially a point in R3 using, actually, sorry, let me take a step back to cylindrical coordinates real quick. So cylindrical coordinates, I'm saying x equals r cosine theta, y equals r sine theta, and z equals z. There's nothing, these are coordinates that are well suited for cylindrical symmetry, cylindrically symmetric regions. So these are regions which kind of, if you rotate about the z-axis, they kind of look the same. So if for some reason it's not the z-axis that's the preferred axis, but say it's the x-axis, there's nothing stopping you from introducing some sort of modified cylindrical coordinates where, say, I take y to be r sine theta and z to be r cosine theta, and now x to be x, right? So just as an aside, there's nothing special about the z-axis. You can sort of do this for any of the other axes. You can do r theta in x, or r theta in y, or r theta in z. Any one of those three is a perfectly valid set of cylindrical coordinates. Okay, so what's going on in spherical coordinates is now we're no longer going to be treating any one of the three axes kind of as a special axis. So in cylindrical coordinates, as we were describing previously, the z-axis was kind of the special axis. Everything was kind of rotating around z. Spheres, right? Spheres don't care about any one of the three axes more than any of the others. They're completely symmetric about all three of the axes in the same way. And so what we want to do is we want to use some new sets of coordinates that don't pick out any one of those axes specifically. So what we're going to do is we're going to introduce some new set of coordinates, and we're going to introduce a way of describing a point in a new way. So I'll introduce spherical coordinates by giving you the three coordinates one at a time. So the first one is going to be rho. So if this point is P, so we don't want to confuse P with rho, so rho is a little bit curlier than P. So what rho is it's just the distance away from the origin. Okay, so it's just this number right here. So rho, we know what the formula is. It's x squared plus y squared plus z squared. So this is just the distance away from the origin. So for example, if we look at regions where rho is constant, that's just going to be giving us spheres. So if rho is equal to 2, that's giving us the sphere of radius 2, all points of the sphere of radius 2. All right, so what's our next coordinate? Our next coordinate is actually going to be theta again. So theta as before. So how do we view theta? What we do is we just project down this point P onto the xy plane and see what angle it makes with the x-axis. So theta is again as before. It's just the angle with the x-axis measured counterclockwise. And so we need three numbers to describe a point in R3. So far we only have two, so we need to introduce one last one. And the last number we're going to introduce is another angle, and it's going to be this new angle called the azimuthal angle. So phi, sometimes I'll write it as phi like this, doesn't really matter, is the azimuthal angle. Okay, so how is it measured? The azimuthal angle is measured as the angle that this line makes, this straight line from the origin up to the point makes with the z-axis. Okay, so you draw this line, you measure this angle phi, and that's going to be your azimuthal angle. So let's take a step back and sort of think a little bit about what this azimuthal angle is really saying. So let's look at the region, or let's look at sort of the surfaces defined by fixed values of phi. So when phi equals 0, I'm describing. So let me just actually, before I do this, let me just say rho is always positive. Okay. So rho is always positive because we're maybe in one way of thinking about it, we're always taking the positive square root here, but just sort of the same reason that we only consider positive radius in order to avoid double counting, we're only considering positive rho, okay? Theta, as before, is always going to be bounded between 0 and 2 pi, okay? So there's nothing changing about theta going from cylindrical to polar coordinates, cylindrical to spherical coordinates. But phi, and you have to think about this a little bit, is bounded between 0 and pi. So I don't want to double count, so I only allow phi to be bounded between 0 and pi. And let's think about that. So an illustrative example is, say I take a point in the quadrant where all of x, y, and z are negative. Okay, so let me take a point back here. It's kind of hard to view in 3D on this sort of 2D tablet right here, but let's pretend this point is back here where x, y, and z are all negative. Okay, so this is my x, y, and z plane. So the point is that from the z-axis down to this curve, I can measure it in two separate ways, right? So if I project this up here, I know what theta is. Theta is measured from the x-axis all the way around the z-axis until here. So this is what theta is. Theta is kind of uniquely determined. But as stated so far, there's nothing telling me how to measure phi. All I said was that it was somehow measured from the z-axis. So I could measure phi this way, or I can measure phi this way, right? In this case, phi would be bigger than pi, and in this case, phi is less than pi. And so in order to avoid double counting, I want to make sure that I'm only considering phis that are less than pi. Okay? So I could have even seen it from this picture. So I could have measured phi from the z-axis in this way, or I could have measured phi all the way around here and measured it from the z-axis in that other way. Okay? But in order to avoid double counting, I'm only going to allow phi between 0 and pi. Okay? And so these are giving us the three separate bounds that the angles and the radius have to satisfy. So let's consider what the different surfaces are which you get when you consider different values of phi. So when phi equals 0, I'm only getting the positive z-axis, right? Phi is measured from the z-axis, and so when phi is 0, any point has to make a 0 angle with the z-axis, so it actually has to lie along the z-axis, and rho in this case is just equal to z. Rho is just telling us how far up along the z-axis I am. When phi equals pi, the other bound for phi, now my angle has to always be pi, and so I'm actually along the negative z-axis. And in this case, z is negative, so z is equal to negative of rho. Finally, another special angle that phi can satisfy is when phi equals pi over 2. And so what points am I getting when phi equals pi over 2? So if I consider pi over 2 is actually just going to be giving this 90-degree angle here, right? And so I'm going to be describing all points in the xy plane when I consider phi to be pi over 2. And then finally, for phi, less than pi over 2 and bigger than 0, or maybe even phi bigger than pi over 2 but less than pi, in all three of these cases, I'm either going to be getting upwards facing cones or downwards facing cones, right? So like this. See, because these points are all described by a fixed phi value. So any point along this cone here, this guy, this guy, this guy, or whatever, they're all making the same angle with the z-axis. And similarly here, this is the case when phi is less than pi over 2. And then similarly here, if I pick any point along this cone, these points all satisfy the same angle with the z-axis, okay? So this angle here, the downwards facing cones are when phi is bigger than pi over 2. So you get either, either you get the positive z-axis, the negative z-axis, the xy plane. So these are the three sort of special pictures, or in all other cases, you get cones for fixed values of phi. And we've already described what the regions are when you get fixed values of phi being, or rho, so rho being the radius of the sphere. Fixing rho is just basically fixing all the points to be a certain distance away from the origin, so you're getting different spheres. Okay, so one last thing to say before we can do some examples of doing these integrals is how do I express x, y, and z in terms of rho, sine, and phi, or rho, cosine, thetas, and phis. Okay, so say I pick this point x, y, z again. So we know how to calculate its expression in terms of cylindrical coordinates. So z is just equal to z. Y, right, was equal to r sine theta, and x is equal to r cosine theta. So how do we express this in terms of spherical coordinates now? Well, theta is as before. So all we really have to do is we need to figure out how to write r and z in terms of rho and phi. Okay. So if this is rho, this distance right here, what we can do is we can drop this angle like this, and we see that this is r, right? R is given by the distance away from the origin. And just looking at this triangle that I've drawn with r, phi, and rho, okay, so one last thing to sort of note is that this is a 90-degree angle right here, okay? So this is kind of at an angle to the surface. So it's not, it's a little bit tough to see, but this is the 90-degree angle here. So this is a right triangle, and we know how to use trigonometry to figure out what our different lengths are. So if this is rho, the hypotenuse, then r is equal to the opposite angle, so it's rho sine phi. And here, this adjacent angle, which is z, is equal to rho cosine phi. And so the angles, or the three coordinates x, y, and z in terms of spherical coordinates, we write it as rho sine phi cosine theta, rho cosine phi. Oops, sorry. Yeah, so this is still a sine phi, sine theta, and then it's z, which is rho cosine phi. Okay, and this is how we express x, y, and z in terms of our spherical coordinates. And then the last thing that we need to know is how do we write our volume element in terms of spherical coordinates. So I'm not going to derive this the same way that I derived polar coordinates or sort of mentioned how I derived cylindrical coordinate volume elements. It's a little bit more complicated because now the pictures are in R3. And so, if you kind of think about what's going on, you'll have this little volume element, which is given by the three angles d phi, and then we have d theta here, which is going to be like this, and then we have separately a d rho, like this. D rho is telling us how far away from the origin I am. This little volume element dv, its expression in terms of rho, d rho, d phi, and d theta is actually a little bit complicated, and its derivation, you have to do some trigonometry, but it's a little bit more complicated trigonometry than we had before. If you want to see the actual derivation, you can go into the more depth section of the textbook, but I won't do it in this lecture. And I'll just sort of state the result. And the result is that this is rho squared sine phi d rho d phi d theta. Okay? So it's a little bit more complicated. You have to remember this rho squared sine phi. But in the end, after you work it out, it's not so bad. Okay, so now that we know what dv is, we know how to express x, y, and z all in terms of rho, phi, and theta, then we can actually start doing integrals. So let's do an example. Okay, so let's do an example for an integral that we already know the answer to. So example 1, let's calculate the volume of 1/8 of a sphere, or of a ball. Okay, and let's give it a radius, right? Of radius r. Okay, so the picture, I draw this ball of radius r, okay, and I'm only considering the first quadrant. So it's this kind of picture right here. Okay, and I know the answer already. I know that the volume of a ball is equal to 4/3 pi r cubed, and I'm only considering the first quadrant, or the first octant, so the first eighth or 1/8 of it, which in the end gives me a pi r cubed over 6. So whatever answer that I get from this triple integral should end up being pi r cubed over 6. So let's set this up and let's work it out. So what are my bounds? Okay, so I'm trying to find the volume. So this is a 1 dv over this. So let's call this region T. Okay, and so what this turns into is it turns into a triple integral where my bounds are in the order d rho, d phi. Well, it doesn't really matter, I guess, but let's do d phi d theta, and the integrand is phi or rho squared sine phi. Okay. So what are our bounds? So rho is the radius of the distance away from the origin. So if I try to measure that from this picture, I start at the origin and I'm in the region to begin with, so that's telling me that my rho starts from 0, and I leave the region of integration when I hit the upper bound, which this sphere is of radius r, so our upper bound is r. As a side note, check that x squared plus y squared plus z squared is equal to rho squared. what I mean is if I write x as rho cosine phi or rho sine phi cosine theta, y as rho sine phi sine theta, and z as rho cosine phi, you should end up getting rho squared, okay? So if I know that this circle, the sphere has radius r, that's telling me that the sphere equation is given by x squared plus y squared plus z squared equals r squared, and that's telling us that in fact rho equals r, and that's telling us that our upper bound for rho is going to be r right here. Okay, so what about our phi bound? Phi is the azimuthal angle, and I'm only considering the first octant, so I'm going all the way from the z-axis down to the xy plane. And this angle is a right angle, so this angle right here is pi over 2. Oops, let's use black ink still. So our phi bounds go from 0 up to pi over 2. And then finally, our theta bounds. Theta is only considering the first octant again, so our theta bounds go from 0 up to pi over 2. And this is the triple integral that will calculate the volume of 1/8 of a sphere. So let's evaluate that. So 0 up to pi over 2, 0 up to pi over 2. And now let's do our rho integral first. So our rho integral, rho is appearing as a rho squared, so this is giving me a rho cubed over 3 from 0 up to r sine phi d theta. So this just gives me 0 pi over 2, 0 pi over 2, r cubed over 3 sine phi d theta. Okay. Next step is the phi integral. Our phi integral goes from 0 up to pi over 2. There's a phi inside of our integrand, so we have to evaluate that. So this is going to be 0 to pi over 2, our bounds for d theta. The integral, the antiderivative of sine phi is negative cosine phi from 0 up to pi over 2 d theta. Evaluating at 0, I get 1. Evaluating at, or negative 1, evaluating at pi over 2, I get 0. So this is 0 minus negative 1, so I just get a 1. So this is the integral from 0 to pi over 2 of r cubed over 3 d theta. And then this last integral, there's no theta, so I just pull the answer down. So it's pi r cubed over 6, and in fact, our two answers ended up matching up. Okay, so that's a simple example, not very much complexity there, but we end up matching up with what we got before. So the last thing I want to do is let's do another example, but let's actually just redo the example we did before. So if you recall, the region T was bounded by z equals square root of x squared plus y squared, and z equals square root of 8 minus x squared minus y squared. So it's some region in R3 and it's bounded by these two surfaces, and I want to figure out what that volume is. So the volume of T will be the triple integral of 1 dv over this region T. And what we need to do is now we need to figure out what our bounds are using spherical coordinates. So let's recall what the picture looks like. So we had this cone, we had this hemisphere, right? They intersected maybe in this little circle right here. And what we were integrating over was this conical part and this spherical part up top. And we need to figure out what our bounds are. So setting up the integral, our integrand is rho squared sine phi, d rho, d, I guess it doesn't really matter again, but let's do d phi d theta, like this. And we need to figure out what our bounds are. Okay, so let's do our rho bound first. So rho is measured from the origin again, and I move outwards and figure out where I enter the region and where I stop, and enter the region and exit the region. Well, I enter the region starting at the origin. The origin is contained inside of this region. So actually what happens is that the row bound starts from 0. And then I stay in this region till eventually I hit this upper bound, and the upper bound is always going to be the equation of the sphere. See, because the cone is really only happening here at the boundary, and the cone is gonna affect what the phi bounds are, but it's not gonna affect what the row bound is. So what's going on is that our row is bounded between 0 and the radius of the sphere, which is radius √8. So our bounds for row go from 0 up to √8. What about phi? Phi is measured from the z-axis. Okay, so let's kind of zoom in a little bit. So phi is measured from the z-axis down to the equation of this cone. So we want to know what the radius is, or what the angle is that this cone makes with the z-axis. So if z equals x squared plus y squared, right, or z equals r, in other words, then I know how to express z in spherical coordinates. That's rho cosine phi. I know how to express r in spherical coordinates. That was something that we did before. This is rho sine phi. And the cone is just essentially the equation rho cosine phi equals rho sine phi. And this is supposed to be true for all rho. So in fact, what we're really trying to solve is cosine phi equals sine phi. And we want to know what the angle phi is that gives us cosine phi equal to sine phi. This is when phi equals pi over 4 or 5 pi over 4. But again, phi is bounded to be less than pi. So in fact, this is pi over 4. So our bounds for phi are from 0 up to pi over 4. And then finally, our theta bounds. Well, that's simple. You know, if you think about what this shadow is in the xy plane, then the shadow is this whole circle. We've already considered that. So theta doesn't have any bounds, and theta goes from 0 up to 2 pi. So if we want to evaluate what the volume of this region is, we just need to calculate this triple integral right here. And we can do that. So setting up this triple integral was the hard part. Evaluating it shouldn't be too bad. So doing the first innermost integral, it's going to be a rho cubed over 3, evaluated from 0 up to √8, sine phi d phi d theta. Okay, so plugging in 0, I get 0, √8. Okay, so √8 cubed, what is that? That's going to be 8 times square root of 8. Or I can just pull out one last 2, and this is going to give me a 0 up to 2 pi, 0 up to pi over 4, but of a 16 √2 over 3, and then sine phi d theta. Okay, so now I need to evaluate my sine phi integral. This is the same antiderivative as before, so this is 16 √2 over 3, negative cosine phi, evaluated from 0 up to pi over 4 d theta. Okay, so what's our two bounds? So this is going to give us negative √2 over 2 minus 1, or yeah, minus 1. Sorry, plus 1, negative 1. And so our total answer, okay, let's just skip a step. Our total answer is going to be, there's no theta anywhere in this expression, so you just pull a 2 pi down. This is going to be 32 pi √2 over 3, √3 times √2 over 2 plus 1, like this. And we can pull this √2 into here so that we recover 32 pi over 3 times negative 1 plus √2, and compare this to what we got before, which was just the same thing as the expression, just √2 minus 1 instead. Okay, so we got the same answer as before. So spherical coordinates are not so bad. Finding bounds for your 3 angles generally isn't so bad. As long as the regions that you're describing are well suited for spherical coordinates, you should try to use spherical coordinates. But you should, be careful. Not everything is well suited for spherical coordinates. So for example, if I'm trying to describe a box in spherical coordinates, that might not work so well. But if I'm trying to describe things that are sort of segments of spheres, or like cones or something along those lines, then spherical coordinates are well suited for that. And so that's kind of all I wanted to say. The last piece of warning, I guess, is all the examples I've given so far have just been volume computations. But again, I need to warn you, not all triple integrals are calculating volumes. Just so happens that the 3 examples that I did today were all volume integrals. But again, not all integrals are volumes. So sometimes the function that you put inside of here is actually going to be an actual function. And what you're doing when you calculate these integrals is going to be something different. So how do I evaluate, an actual function? Well, you use these expressions that you got for x, y, and z in terms of rho, phi, and theta, and you plug that in, and you'll get some complicated integrand, but that'll be the integrand that you have to calculate to evaluate the integral. And you may be getting positive numbers, you may be getting negative numbers, but in the end, whatever number is that you get is going to be the answer. And hopefully you do it right and you get the right answer. Okay, so that's all I want to say. So keep an eye out in your email for future contact. I'm going to try to set up some streaming things so you guys can see these lectures and ask questions as I go along. And so, yeah, just look at your emails and hopefully this works out better going forward. Okay, thank you. Bye.